Your B field, your force, and then current, So you have to have an opposing force for the y direction in order for it to be canceled. Yeah. But I don't know, because I took it like right at the top, right? So it looks like I'm flipping people off.
I took it from a lab. It's working really well.
Yeah, it's like ... question mark, I think. Very open-ended.
Okay, so you guys just figured out, or you're working on figuring out how to know, or what direction the force must need to be to cancel the gravity, right?
Yeah, that's what I was thinking.
I agree. So the force must be upward, which means. So did you figure out what direction the current must be then?
Well, I took it at the top of the wire because, so current, field, force. We know the force needs to oppose gravity for it to reach terminal whatever velocity. Pretty much for it to be a constant acceleration or whatever, 0. Okay, so then force up, field in, top of the wire, current this way.
So yeah, so then the current must be going to the right on the top wire, is that right? Okay, agreed. But is that happening? Because there wasn't a battery or anything in this problem. Like the current isn't there, so there must be something in the problem that's causing the current. So what would
induction? We'll have to have flux.
There you go. We both have it. Perfect.
It.
So you already figured out probably what the current must be, just because we know that this problem is going to work out. But then, so let's figure out how that. Let's figure out it another way then. So you figured out the current must be to the right. At the top, because that's the only way the force would be upward on it, right? But why? But is current to the right at the top? Is that supported by Lenz's law, basically, right? So we're losing. Well, what's happening to the field or to the flux?
Well, because we're pulling it out, right?
Okay.
So then we're going to be putting more in that way.
Right. So we lost the field into the board as we're losing x's, right?
Yes.
As we go down.
Yes.
And so we need to put those back in. So that's the induced field. The induced field is in.
Yes.
And that means that the current will go around that way, which is exactly what you said. Perfect. Yay.
There it is.
2 ways. Let's see. You mean in the next bit there?
The part where it says prove that it's equal to this, and we did.
And that is equal to that.
Yeah.
I guess he's just saying that. So recall that the stuff in front of a sine function. Do you remember what that means? Like if you have 10 sine of t or something, do you remember what the 10 means in the context of trig?
10 times the sine?
Yeah. Do you remember what the 10 means? The thing in front.
Shift it?
It's the no. That's a thing inside of the sine. But what I'm getting at, and I think you know what I'm just asking it poorly, is it's the amplitude. So like you draw the wave, and that's where the tip goes up to, in my example, positive 10 and then down to negative 10. So a lot of the time what they'll do is that if in deriving these equations, they'll just lump all the stuff in front of a wave together because that's the amplitude. So what he's trying to tell us is apparently the amplitude is equal to 2 pi f BAV. And so he's calling it E naught because it is a voltage, because sine is unitless. So whatever that stuff is apparently is the max voltage that you get to. It's just sort of an odd assortment of variables, but it makes the voltage.